Okay, so in this problem over here, let's read it. It says a vertical plate is partially submerged in water and has indicated shapes. I'm going to say it looks like a semicircle to me. Find the hydrostatic force against one side of the plate. All right, the hydrostatic force problem. I'm put a coordinate system and help me set the integral up. Put this here, I'll call this the x-axis. And I'm going to call this the y-axis over here. All right? So the next thing I'm going to do is, to talk about the equation. Whoops, sorry about that. The equation of the circle. I'm going to say this is the point 0, 0. And this point up here, that's going to be, well, the x is going to be 0. And that's a 6-meter diameter, so it's going to be a 3-meter high, and that's the radius. I'm going to write the equation of the circle down. It's going to be x minus 0 squared plus y minus 3 squared is equal to r squared, and r is 3, so 3 squared. Let me just simplify a tiny little bit. X squared plus y squared minus 6y plus 9 equals 9. I'm going to simplify a little bit more. X squared plus y squared minus 6y is equal to 0. All right, I'm going to get my eraser out and get rid of this preliminary information here that I don't need anymore. So I have a relationship between x and y. This was why do you need that? Hydrostatic force is going to involve area. So I'm going to talk about area now. I'm going to do it in slivers. And the way I'm going to do the slivers is I'm going to do, let's draw the picture in. I'm going to do a sliver this way. And the reason to do this over here, what I like to do is I like to get the differential first. And the differential of this sliver over here is going to be dy. All right? And what's the, to me it's related to that circle, but this over here is x. And I'm going to tell you that x is greater than 0 in this case over here. Maybe greater than or equal to 0. So that means this entire distance over here is 2x. All right? I'm taking x to be a positive number. So we need to solve this equation for x. Let's put that down. X squared equals 6y minus y squared. And so x would equal plus or minus the root of 6y minus y squared. Well, remember I said x is greater than 0, so I take the principal root, which is positive. So let's write this down. So I get 2, right? I'm talking about point that out to you again, 2 of the x's, and I'm picking the principal root, so because I'm taking the x to be greater than or equal to 0. So it's going to be 2, the root of 6y minus y squared dy. Now, there's other things to put down, but let's not worry about that yet. Let me just worry about what the limits of integration are. And it appears that I'm going to say I'm starting at the bottom and moving my way up. And this is 1 meter. The water's 1 meter. I'm going to say the water's level, by the way. I realize it looks like curved to me, but I'm going to say it's level. So I'm going to say, to simplify the problem, by the way, I'm going to say it looks like it's going from 0 up to 2. All right? So I'm pretty comfortable I got that part done. I can get my eraser out. And I want to just talk about the, what's causing the pressure over here. It certainly has to do with distance, but it also has to do with the water and the gravity. So let me write these things down for you. I'm going to write gravity, and they're in the meter, so it's an MKS system. So gravity, maybe I shouldn't use the letter G for that. I'll say gravity, G-R-A. The gravity is 9.8 meters per second squared. And I'm going to say the density of water. Well, one thing I can remember, at least I'm pretty sure, the density of water is 1 gram per cubic centimeter. All right, but you know what? I see meters and centimeters now. I gotta get rid of that. All right. Now we're in what's called the MKS system. So MKS, which is meters, kilogram, seconds. Well, I got seconds, I got meters, but I got these grams and centimeter cubed. So what I'm going to do is I'm going to say there's 100 centimeters to every 1 meter. All right? I can write it as 10 squared. That's 10 squared is 100, right? Is 1 meter. But I want centimeter cubed. So it's going to be 10 to the 6 centimeter cubed is the same thing as 1 meter cubed. All right? So what am I going to do over there? I want to get rid of the centimeters. I'll write this over here. And I'll write this over here. It's density of H2O now. Density of H2O. So it's 1 gram per centimeter cubed. So I now know that there's 10 to the 6 centimeter cubed in every meter cubed. Now, certainly I want to go from grams to kilograms, and that's an easier one. That's what's so nice about the metric system. It's based on powers of 10. And there's 10 to the 3 grams, or 1,000 grams, in every kilogram. All right, so the density of water, I think I got it now. 10 to the 3, looks like 1,000. It's not that bad. So the same thing as 1,000. Let's see if I'm saying that right, by the way. 10 to the 3, 10 to the 3. Yeah, 10 to the 3, 1,000. Centimeters are canceling off. Grams are canceling off. So 1,000 kilograms per meter cubed. All right? And then, I'm talking about this is the density of it, and I'm going to be multiplying by, let's see, 9.8. Right? So I'm going to take the gravity times this kilograms per meter cubed. And what are you going to get? If I did that, I'll write this on the side for you. You get 9.8 meters per second squared, and times 1,000 kilograms. This was known as dimensional analysis, meter cubed. All right? Let's write that number down. And that number, oh, by the way, the volume I'm sorry, I misspoke by not volume, but the area is meters squared. So we'll talk about the unit on the integration a little bit later. So I'm getting 9,800. See if I said that right. Yeah, 9,800 kilograms. Second squared. Metered squared, I'm sorry. I'm just going to write the number in now. I'm going to write 9,800. Now, the next thing I got to worry about is the distance. All right? And that's always an issue. I'm looking at that and the distance. I'm going to say at 0, it's 2 meters down. So I'm going to check it out too, by the way. So I'm going to say 2 minus y. So at 0, it's 2 meters down. So that makes sense to me, by the way. All right? So at 0, it's 2 meters down, and then at 2, there's nothing there. So that seems to be pretty good to me. All right? Now again, I want to just say that I think I have the integral. All right? I'm going to start to erase things, by the way, because I realize I did some work that that some students may not have needed done because maybe they're just more familiar with this problem. All right? But I think I'm getting really close to an answer over here. And before I do that, I just want to make sure I'm okay with units and stuff. By the way, it's okay to use a calculator in that integration, by the way. Not that you have to, but I think it's okay because I think they're asking to approximate it. I know it's multiple choice answer. It's all approximate answers. Clearly you need a calculator for something like that. At least in this modern age you do. So let me just talk about units again. I got kilograms, second squared. I got metered squared. Area is metered squared. And then got another meter over here. And let me see how we're doing over here. Kilograms, metered, second squared. All right? And I'm pretty sure it's Newton. All right? So I think I got that part done. What I did not do is the integration. Before I do the integration, though, and I want to just make sure that in the key I have things written down for you that represents what I think I'm looking at. Let me get my eraser out. I think I did my dimensional analysis okay. I think I can remember what newtons are. going to go for it. And I'm going to look at it now. And let's take a look. I'm definitely seeing dy. I'm definitely seeing this business over here. I'm definitely seeing the 2 minus y. I'm definitely seeing the 0 to 2. Now, they have something different down. They have 19,600. Well, if you do 2 times 9,100, you get 19,600. So I'm pretty comfortable there. Now, granted, I'm looking at the number, and I would use a calculator, and I did use a calculator, by the way. This symbol over here is saying approximately this number over here. And what's the unit on that? Well, we just talked about that. It's kilogram meter per second squared, and I believe the name for that is Newton. I could look that up. Yeah, I see Newton's being listed. And I'm looking for the number. What number am I looking for? 66980, and this is the only one that matches that. All right? And again, we're getting pretty good results there. And again, the way I did this, I used a calculator, and the calculator that I'm using is called Sage. And I do recommend that you look into learning how to work a computer algebra system. And Sage is an excellent open source example of a computer algebra system. Thank you.